to be from the epoch of formation, the outside influences and so on. And then we were starting with what I've called the fundamentals of stellar dynamics, which I'm going to continue today. And then I will start talking about stellar orbits and perhaps we get to Jean's theorem, perhaps only tomorrow. So this is how far we went yesterday. This is the collisionless-Boltzmann equation that governs the evolution of the distribution function in phase space. You recall the distribution function depends on position and velocity, six-dimensional phase space, and it's conserved along the orbital trajectories in phase space given by basically the velocity and the potential gradients. And together with the Poisson equation, this is a complete and self-consistent system, which in principle you can evolve, only that it's quite hard. So F contains all the information about the stellar system that you might care to know about. For example, if you wanted to determine the mean streaming velocity of the stars in a particular region of space, you would work that out from the distribution function by averaging the individual stellar velocities over velocity space in that spatial volume, and that gives you rho times the streaming velocity in this direction I here. And similarly, you could determine the mean square velocity dispersion of stars around the streaming velocity at that point by considering the average of this quantity Vi minus Ui, where Ui is this mean streaming velocity, and Vj minus Uj, which is the same except that it's a different component, and that gives you a number which is given by rho times sigma ij. So there are three phase space directions, and there's therefore this tensor here is a 3×3 matrix. It has 9 components, of which, however, only 6 are independent. So because you can interchange these terms here. So now let's go to what I had called here stellar hydrodynamics. This is the moment equations of the collisionless-Boltzmann equation. And let's start with the zeros order. So we simply take the collisionless-Boltzmann equation df dt equals 0, and then integrate that over velocity space. And then if you do this, and I don't want to go to the details here, you can read this in Binion Germain, you get an equation that has this general structure here, which is a partial derivative coming from the partial derivative of f plus an advective term, the mean streaming velocity times the density is equal to minus rho times the divergence of that velocity field. And then if you do this for the first order equation, the so-called momentum equation, or the Jean's equation, as we'll see, you multiply the collisionless-Boltzmann equations by v. I've written this as a vector here. And then you integrate over velocity space. Then you end up with another moment equation, which has a structurally similar form. Again, you have a material derivative, d partial by dt, plus u dot del times, and now not the density, but the mean streaming velocity. And that is equal to then this right-hand term, which is the potential gradient, plus one of the density times the derivative of this velocity dispersion tensor, more or less. You can see this is a scalar equation, but this here, since I multiply it by a vector, is a vector equation. So these are the three equations, really. And in each of these three equations, this here is the derivative scalar product with this tensor. So that's 3 terms in each of these each of these component equations of this vector u. And then you can keep going. You can also multiply by higher order moments of velocity and get yet more moment equations of the collisionless-Boltzmann equation. Now there's a number of points to note here. First of all, you can see this gives rise to a hierarchy of equations depending on the order of velocity with which you've taken the moment. Now the hierarchy isn't closed in general. the reason is that, well, the formal reason is you can see that in the evolution equation for the zeroth order moment, the density, you have the first order moment on the right-hand side. So you can solve this if you know first order moments. In order to know the first order moment, you have to really solve that equation. But then you're getting into issues about the second order tensor and so on. So for whatever equation you solve, you need more information. That means the hierarchy isn't closed. That's the formal reason. The underlying physical reason is, or mathematical if you like, is that you're trying to approximate the velocity independence of a function by a set of moments. And of course, if the velocity structure is arbitrary, you need an infinite number of moments in order to characterize that velocity dependence. So it can't be closed mathematically. And so there's different, you will see in a moment, this is also why they're called equations stellar hydrodynamics, that this terms here is a bit like a pressure gradient. If you had a fluid, then there would be what's called an equation of state that would relate the pressure to the density and maybe some temperature or energy term. And if you were able to specify the energy by energy equation, then that would close the system, and you could then solve it. But in these stellar dynamical problems, there is no equation of state, and therefore this doesn't work. So one has to make assumptions to close the system, and we'll come to that in a moment. Now, the other thing to notice here is that's quite an important point, is if you found a solution for the phase-space distribution function evolving in some particular way, then these are exact moment equations, and therefore the moments must satisfy them. And if they don't, then there's something wrong. Yeah? So in this sense, the relation is clear. It's not true in the inverse direction. If you found a solution to the Jeans equations, then it doesn't mean you found a solution to the collisionist-Boltzmann equation, because you've made certain approximations about closing the system. And it's not clear that this solution has any solution in the full phase space. Especially, one thing I think I haven't said so far is this phase space distribution function gives you a probability for the stars in phase space, or if you like, a phase space density, and there are no negative stars, and so this function must always be positive. And so there are examples where you find solutions to the Jeans equations, but they don't have a positive distribution function corresponding to them. And if you go to the details, you may find that some of these solutions turn negative in the phase space distribution function, which are unphysical. So there's this issue about the moment equations. So let's now take some examples. So this is now the spherically symmetric case. So what we're assuming here is in this velocity space, that corresponding to the spherical coordinate system, that we must have the two angular velocity dispersions equal. We can have a different velocity dispersion in the radial direction. And if we also suppose that we're looking at a time-independent system, then we cannot have time derivatives, and we also cannot have streaming velocities because of the symmetry. And then the entire equation here, these in principle 6 independent equations, boil down to this one equation, which is the equation here for relating the two velocity dispersions sigma r squared and sigma theta squared, which actually must be equal to sigma phi squared in full spherical symmetry, to the density and the gravitational potential. Now again, you see that this equation isn't quite sufficient to determine your system, because supposing I know the density and I know the potential, then there's two unknown functions, sigma r squared and sigma theta squared, but there's only one equation, and so I can't determine both of these quantities independently. So what I must do is make some additional assumption, and one of the possible assumptions is that I suppose the system is isotropic, means that sigma r squared and sigma theta squared dispersion are the same. In which case, then this equation can be solved very easily, and the solution is this one here. Now, this term then goes to 0, and I just integrate this potential gradient from r to infinity, and that's my rho sigma squared. So, however, not all systems are anisotropic, so this is what I just said. So in general, what one does is one defines anisotropy parameter, which is due to Binney originally, and it is defined in this spirit of the Jeans equation as the difference from 1 caused by a difference in these two loss dispersions. If you then put that into the equation, you can go back here to see, then this essentially has sigma r squared, and then it has sigma theta squared, and so this is where the beta comes from in this case. Then you can now put that in, and you could also substitute the potential gradient by the mass distribution for a spherical system. And then you find, after a little bit of algebra, that the mass interior to R from the Jeans equation is then given by basically sigma r squared R over G times the sum of those logarithmic gradients in density, the loss dispersion squared, and this anisotropy parameter beta, which in principle can depend on radius also. So for mass determination purposes, this is why I'm going through this, we'll use that later. It's not important that the density of stars is the density corresponding to whatever causes the gravitational potential. All that's required is that you have a consistent tracer distribution of stars, which give rise to the density you're looking at here, and the velocity dispersion and the anisotropy parameter. And then the potential, in some sense, is independently determined. So, for example, you can use, we'll do that later, you'll use a particular tracer distribution in the galactic halo in order to determine the mass of the galactic halo interior to R. And that includes the dark matter, even if your tracer density distribution is completely free. As long as it's consistent and well mixed and in an equilibrium in the gravitational potential, then this is a useful equation to determine the total mass. However, as we said, there's one more parameter than you can actually determine from the equation. That's the beta parameter here. You can solve it for if the system is isotropic, then and I can measure rho and I can measure sigma in principle, then that equation gives me mass. But if I also require the anisotropy parameter, I have some uncertainty. And so there are various ways of trying to get around this. You could either make some assumptions about the anisotropy parameter, try to verify this from the projected velocity distribution or so. Or you could make some other, if you assume that the tracer density actually does correspond to the source of the potential, then you can get around it in some different way, as shown by Binney and Marmot. Okay, now I want to sort of illustrate quickly what is meant by this stellar dynamical pressure. So we have this spherical symmetry here, this sort of pressure term, and then we have this anisotropy term. And so what this pressure term basically means is it's just a kinematic effect. Supposing you have a box here where in some region of the box you have a higher density, but the same velocity dispersion, or likewise you have the same density and a higher velocity dispersion, you can see that this generates a gradient in the quantity rho sigma squared. And the effect of that gradient will be that if you did nothing else, that the particles would move from the region where there's higher density in the mean to a region of lower density, or they would move from a region of higher dispersion into a region of lower dispersion in the mean. So you must do something else about it, and this is what the potential gradient does. The potential gradient actually makes it harder for stars to move up in the potential, and so that's how you can balance this kinematic effects. The difference to so in some sense this acts like a hydrodynamic pressure, but there's one important difference, and that is because, as we said, the stellar system is collisionless. There's no way, in principle, to equalize the dispersion in different directions if the system is time independent, and therefore, in principle, you can have this what's called anisotropy between the velocity dispersions in different directions in your system, and that's something that fluids don't have. So now let's go to the axisymmetric Jeans equations. Now here we end up having three equations. That's because of the various mixed moment that remain under symmetry assumption. But these three equations now relate six quantities for us. You can see what these six quantities are. There's the radial velocity dispersion, VR squared. There's the mean square velocity in the tangential direction around your symmetry axis. And there's the mean square velocity dispersion in the vertical direction along the symmetry axis. And then in addition, there are these mixed moments of the velocity dispersion tensor, which you remember this sigma squared tensor had in the beginning. And there are the mean values of VR and VZ, VR and V phi, and V phi and VZ. So if now you assume that you only have azimuthal streaming motions in your system, and that the sigma tensor has two equal quantities in the meridional plane, sigma r squared and sigma z squared, then all the mixed moments will vanish by these assumptions, and you end up with only two independent equations, which are now given here at the bottom. And you can see that now there's essentially the dispersion in the meridional plane, which is determined by the vertical potential gradient in this equation here. And once you know this sigma squared, then you can use it in this equation, and then what you can in addition solve for is the V phi squared RMS term. And so that's written down on the next slide here. So this is the two equations again. Now let's start with this equation here. This we simply integrate like in the spherical case, and then you can determine what sigma squared of R and Z must be. So that's essentially then the potential gradient times density integrated vertically up to infinity. And then the first equation gives you then this V squared term, which is given by this expression. And that's just an algebraic reshuffling of the second equation. So in that sense, now you've solved your system, but there's still one uncertainty, which is not taken into account at this time, which is what the mean streaming velocity is that you have around your symmetry axis. And that is, in principle, not fixed by your potential, because supposing you set up a system that satisfies these equations and that has zero streaming velocity, you can always take some stars and reverse the directions of motions in the azimuthal direction, and you will still have an equilibrium. You will at that moment not change the V phi squared, but you will change the mean streaming velocity and the velocity dispersion in the azimuthal direction, in such a sense that this quantity here remains constant. So there's some ambiguity as to these what's it called, semi-isotropic models. There's many models for the same density distribution and the same potential, which differ by the streaming velocity field. So I wanted to tell you something about jams, because this is these are models that have been used quite often recently, and were, I think, invented by Michele Capellari. So this was based on looking at Schwarzschild dynamical models of the cores of early type galaxies, or the inner effective radius or so of early type galaxies, where the Saran team had made observational velocity fields. And so from these Schwarzschild models, you can sort of, once you make an orbital distribution that satisfies the predicted kinematics, you can look into these models and ask yourself what the velocity ellipsoids look like in the meridional plane here. This is Z and R. These are axisymmetric models also. And then this is a typical example of these velocity dispersion ellipsoids. And you can see that in this direction, on the major axis here, you have these ellipsoids in the sense that the radial dispersion is larger than the vertical dispersion. And then as you go around the circle, you can see that the principal direction is sort of more aligned spherically than cylindrically. But as you go to the minor axis, you find the same kind of velocity ellipsoid, where now the main velocity direction is horizontal again. That means perpendicular to the axis, and now the radial dispersion is smaller than this one here. And the change of axis ratio of these ellipsoids is just such that this transition occurs this way, even though the principal directions of these ellipsoids are more elongated along the spherical axis than on the cylindrical directions. And so what the assumption of these jams is now is that let's forget about the fact that these ellipsoids are oriented in spherical direction. Let's assume they're all oriented in the cylindrical coordinate system like this. And let's also forget about the fact that their elongations vary as a function of angle here. Let's assume they have always the same orientation, always the same ratio. And so this is these assumptions. Then if you make this assumption, then this mixed term VR Vz will be 0 because of the cylindrical velocity ellipsoid. And then the VR squared is assumed to be always the same constant times the vertical dispersion Vz squared. So that's what I said just geometrically now in formulae. So if you put that into the Jeans equation, again the same axisymmetric Jeans equation we had just now, then you have here this factor B, which is the difference between VR squared and Vz squared, which comes in here and here. And otherwise, it's also two equations that are simple because the mixed moments have disappeared from the equations. So you can solve these equations just like the previous case. And the solution now is in the vertical direction the same, but in the radial direction it is somewhat different because of this factor B here in the equation. You still have the problem you don't know. This doesn't specify the mean streaming velocity. You have to specify those from other considerations. But if you do, and there's a rather elaborate machinery behind this, then you can see that the velocity and dispersion maps. Here's the velocity dispersion map, and here's the velocity map predicted by these models is actually quite similar to the observed velocity dispersion and mean velocity maps in those galaxy cores. And there's a few examples that I've copied you here from Capellari's paper. And so even though you make some assumption that's in principle not correct, as you see from these ellipsoids, you find that the mean anisotropies of these galaxy models is actually not so different, only by a few percent, from the mean anisotropy of the full orbit models that we use to analyze the galaxies beforehand. So it's a useful means to use the Jeans equations, given these assumptions, to analyze the data of a certain class of galaxies. It's not that the galaxies have to be that way, but it just so turns out that they are approximately that way. And so therefore, these models have become a good way of describing them. Now, about the orbit models, we'll talk more later. So just be patient for those. So that's GAMS, Genes Anisotropic Models, and they're being used quite a lot now. So now let's come to another ingredient, the so-called tensor-viral theorem. You remember that at the beginning of last lecture, I was deriving the scalar-viral theorem for you from the n-body equations of motions. Here is the tensor-viral theorem, now derived from the collisionless Boltzmann equation. And what you do now is you write df dt equals 0, means that the change of distribution function is constant. There's no change along the orbits. You multiply that by xj and vk, and then you integrate over the full phase space. And then you end up with an equation that has this very simple form. There's again a second derivative, and there's 3 terms. And these 4 terms is, first, the ijk is the so-called moment of inertia tensor. That's just jxk rho integrate over position space. There's the streaming kinetic energy term, tjk, which is the mean streaming velocity uj uk times density integrate over d3x. There's the pressure tensor, which is the sort of dispersion velocities around the mean streaming velocity in the usual quadratic sense, integrate over d3x. And then finally, there's the potential energy tensor, which is the integral d3x times xj d phi dxk. So that's potential energy times the density. So it's not entirely trivial to arrive from here to here, but you can read this in Intermain. It's mathematical manipulation. So it's more important what this means. First of all, you see we've integrated over d3x and d3v. So we're talking about some quantity that is true for and some equation that is true for the entire system. We're not differentiate between center, inner parts, half mass radius, and outer halo or something. This is something that's true for the entire system. And secondly, from looking at these equations here, you can see that this is a tensor equation that has 3 by 3 terms. In other words, in principle, it's nine equations, but of course, also those are not all independent, just like in the previous case. And what it relates is like in the scalar viral theorem, it relates in equilibrium where this I2 dot term should be 0. It relates the total kinetic energy here split up into mean streaming velocities and random velocities, i.e. Dynamical pressure, to a term which governs the potential terms. And so it's in some sense a generalization of the scalar viral theorem. And if you take the trace of this equation, then you actually recover the scalar viral theorem just as we had it last time. So contrary to Jean's equation, which are valid at each spatial coordinate x, this is a global equation. The one thing perhaps that one has to say also is that if you can't integrate over the entire system, then you have some possible problems, because in principle you should include some surface terms, and that's often not done because one doesn't know how to do it. But it means if you look at finite systems, then you have some error in this. I think this is what one needs to keep in mind. So let's go and do an example. So let's take an axisymmetric system where the z-axis is the symmetry axis, and let's assume that system is in equilibrium, so I can set these inertia tensor terms 0. Then because it's axisymmetric, I can put the xx and yy components of all of these quantities equal. And when you look at it, then also the mixed terms turn out to be 0. So ij is equal to 0 when I is not equal to j. And so there's two remaining non-trivial equations in this case, one governing the vertical virial equilibrium and the other governing the horizontal virial equilibrium. And that, of course, doesn't depend in which direction in the plane you look. And they're given by these very simple equations, so that the kinetic energy terms in xx and the potential energy term in xx add up to 0. And the same is true in the vertical direction. So what one can do is one can divide one equation by the other, and then one can use a fact that is very convenient in this respect, and that is if you assume your mass distribution is spheroidal, in other words, it's just a sphere flattened in one direction, then and the axis ratio are given such that A equals B, the two long axes are the same, as we said, oblate symmetric, and the short axis is shorter, then the ratio of these terms turns out to be independent of the precise density profile and is only a function of the axis ratios. Now that function is not a simple function, but you can approximate it by this power law here to some accuracy, about axis ratio to the 0.9 or so. So then you now know this ratio here, and therefore you also know this ratio on the left-hand side. So now we can do this in three separate cases. Let's, in the first case, assume that my pressure tensor is isotropic. That'll be like the semi-isotropic models in the gene sense, plus the additional condition that the streaming velocity is just such that the velocity dispersion is really isotropic. Then in the vertical direction, you can't have any streaming, so I can put that to 0. And so the only pressure is in this isotropic term is m times the mean square velocity dispersion. And then the sum of the kinetic energy terms in the streaming, in the equatorial plane directions, is then 1/2 times the total mass times, let's say, the mean streaming velocity squared. And this is sort of defining what I mean by sigma squared and by v squared. So it's not really something new. It's just a redefinition using the symmetry. And then I can use this ratio of kinetic energy terms, as I had on the previous view graph, to write what v over sigma is. And since I'm having squares here, I'm getting a square root. And the potential energy term on this side here, minus the 1 here, appears on the right-hand side under the square root. So what it tells you is that if I have a spheroidal system with an axis ratio A to C, which will be greater than 1, then I need a mean streaming velocity in addition to an isotropic velocity dispersion, which is given by this expression, and that's the global value, right? Not local, it's a global value. Now you could relate that to some observational numbers, as people have been doing. For example, one of the older conversions was the maximum velocity at where that was reached in an elliptical galaxy, seen edge on, divided by the mean velocity dispersion within the half mass radius or so. And then if you put in numbers and you say, let's suppose my system is spheroidal by an axis ratio of 0.7 to 1, then the typical rotation velocity you need in order to flatten such an isotropic model is about 0.8 times the mean velocity dispersion. Now, similarly, you can say, let's suppose my system doesn't rotate at all, and all my difference in the kinetic energies between the z direction and the equatorial direction is in a different velocity dispersion. That's anisotropy. And as you remember, this is something that stellar systems can do, which fluids can't do. Then you can write the equation this way. So now the ratio of the kinetic energies is simply given by the pressure terms, which is m sigma x squared divided by m sigma z squared, or the other way around. And then again, your potential energy ratio is given by this simple expression of the Axelos ratios. And now here out comes the ratio between your global velocity dispersions, sigma z to sigma x. And it turns out for the same case, C over A is 0.7 or so, then your velocity dispersions have to be different by a factor of 0.87. So that means you can make the same self-consistent spheroidal system by either keeping it isotropic and adding a rotation in the equatorial plane, and then you need that sort of number here, about 80% of sigma for axis ratio 0.7, or you can make it self-consistent by simply reducing the vertical dispersion or enlarging the equatorial dispersion by this factor here, 0.87. So one thing it tells you is that it's actually not so hard to do it by anisotropy, because that's after all only a 13% difference. But if you want to achieve the same kind of flattening of the system by rotation, you need to put in the order sigma in terms of, so it's rather a larger effect. And then you can also do it by a mixture of rotation, anisotropy obviously, and there's a little formula that relates the velocity, the mean rotation velocity that you need, and the dispersions, again to this ratio of potential energy terms. So what the tensor-Vierel theorem gives you is some simple method of estimating what the distribution or what the ratio of the energies in the different directions of motion have to be if your system has a flattening of a certain amount. So it's very useful for making quick estimates of such velocity ratios. Okay, so finally I want to illustrate this by this diagram here, which comes from Cormandy and Illingworth originally in about 30 years ago. But this is an update that Cormandy did a little while ago. And so what's plotted here is the axis ratio of elliptical galaxies, bulges of spiral galaxies of various kinds, versus the ratio of the maximum rotation velocity to some suitably defined velocity dispersion. And then in this line here is the so-called oblate isotropic line, which is the line you get for this first case I showed you, this one here. So you see here, I took V over sigma in this case. This is basically C over A is 1 minus epsilon. And so you can see that this gives you a relation between this V over sigma and the C over A. There's some conversion to observed quantities, but otherwise that's this line here. So that's the line where all the velocity dispersions are isotropic, and for the given axis ratio here, the system has just enough rotation to make it isotropic at that axis ratio for an oblate geometry. And then there's various points here. The crosses are elliptical galaxies, massive elliptical galaxy, let's say. There's various kinds of bulges on here, which the so-called classical bulges, those one supposes are made by mergers. That's the open circles. And then there's what Cormandy calls the pseudo bulges. We heard about that yesterday already. So that's the ones that one presumes are made from disks of the galaxies in which they live in. And you can see that the classical bulges rotate faster than the elliptical galaxies in this plot, and the disk-made bulges, they're sort of up here, they rotate faster than the classical bulges. So that's one way for which one thing you can use the tensor-Vierel theorem for. Okay, now I want to change topic and come to the stellar orbits. So if you want to ask some questions to this, maybe that's the right time.
I have one question. This particular diagram, what does it mean with respect to the relative importance of rotation and anisotropic pressure for maintaining equilibrium in these different type of systems?
Okay, so that you can see that an object that's on this line is consistent with isotropy. No? An object that is below this line must have some anisotropy, and likewise, an object up here must have some anisotropy.
Right. So
but the details are not quite trivial.
But the solid line you mentioned before that corresponds to the previous model, in which there is also some anisotropy.
No, the solid line was the isotropic case. Yes. Mm-hmm. So this is, for example, is the line where there's no rotation. So that was one of the simple cases I was treating. Then this is the isotropic case, and then of course the mixed cases as well. Everything okay? Good. So let's now come to the second part, which is about stellar orbits and Jeans theorem. And I want to start again with a simple case. But first, let me tell you what I want to do. So I want to briefly tell you about orbits in spherical, axisymmetric, and triaxial potentials. A little bit about orbits in disks and rotating potentials. I want to explain you briefly about integrals of motion, about action angle variables, and integral and non-integral potentials. Not at the level of detail as in Binion domain, you may understand. And then I want to come to Jeans theorem, one of the principal means of constructing equilibrium distribution functions for spherical and axisymmetric systems. I mean, it's more generally applicable, but that's what it's been usually used for. And then finally, I want to tell you a little bit of how you construct such Jeans equilibria from so-called self-consistent dynamical models and treat Schwarzschild's method and so on briefly. Okay, so let's start with a simple case. But let's first recap what we've learned before. So the two-body relaxation time is much larger than the age of the galaxy. Therefore, we can neglect potential perturbation from individual stars. Okay, we just never consider them anymore. We consider orbits, therefore, in mean field potentials. Then, as we saw last time, because of the formation and accretion history of the Milky Way, in reality, such potentials could very well have a certain degree of bumpiness from dark matter subhalos, spiral arms of the disk, and all sorts of things. But it's quite customary as a first step to neglect all of this and now take simple, typical smooth potentials, which you feel are a reasonable approximation to the galaxy, and then study the orbits in these. And then later, one can add perturbations to these simple potentials in order to see what that does to the orbits in those potentials. So that's why it's useful to study the simple systems, because it sort of gives you a general idea, and then later you worry about the perturbations. So here's simplest of all cases, the spherical potentials. You know that in spherical potentials, orbits are confined to planes. That's because the angular momentum vector is conserved, and it has three components and therefore a direction, and the orbit evolves in the plane perpendicular to that angular momentum vector. Essentially, you can write down everything. At least you can't maybe do all the integrals, but for the most part you can. So this is the equation of motion here, radial potential gradient. The angular momentum is constant. You can write the energy equation. You can write the orbit equations. So you divide, use the identity that d by dt is like L over r squared d by d phi, which comes from this equation here. And then you can transform the equation of motion in time to one as u by d phi, where u is 1 over r. Now you've done this. This is in Goldstein, I think. And so you can actually write down the equation for the orbit in this way. And then it depends on the potential whether you can actually integrate it analytically or not. But in any case, you can do it numerically. And so you find that these orbits are typically rosettes. So they're confined between an inner, let's say, pericentric radius and an outer apocentric radius. And you also find when you integrate this equation here for the delta phi as a function of excursion of the orbit, that the typical delta phi per radial evolution for orbits in galactic potentials is like between pi and 2 pi. And I think it's pi for Keplerian and 2 pi for harmonic potential, which sort of cover the degree of concentration that's typically found in galaxies. So the orbits can be calculated quasi-analytically. They are typically rosettes. There's some set of measure 0 that's exactly radial. All orbits have 4 isolating integrals. We'll come to that later. That's the energy and the 3 components of the angular momentum. And then again, as we'll see, you can define action angle variables, JR, J theta, and J phi. And then there's a 4th integral which sort of defines the degeneracy in that space. Okay, so now we come to integral potentials. This is a spherical potential. This is an example of an integral potential. It's even an example of a separable potential, which is one where the Hamilton-Jacobi equation separates in suitable coordinates. You may remember that from your classical mechanics. And so, therefore, given that I can separate the Hamilton-Jacobi equation, I can integrate the equation of motion, at least in principle, by quadrature, as one says. So these separable potentials are a subset of integral potentials. And so let's see what integrable potentials are. So here we write the Hamiltonian. This is a Hamiltonian system. That's our galaxy potential here. This is the square of the momentum. And the equations of motion, if you remember, is that x dot is dh by dp, and p dot is minus dh by dx. So now we can say what it means to be an integral. So suppose I have another function I of x and p. That's called an integral of motion if it's constant along every orbit. So I work out d by dt along the orbit, and I'll find that function is constant, so the derivative is 0. So the integral I and the Hamiltonian A are called in involution if and only if this Poisson bracket here is equal to 0. Now the Poisson bracket is equal to the total time derivative, and the Poisson bracket is expressed by this expansion here. And then if you put the equation of motion in, you will see that that actually means that di by dt equals 0. Now, one thing to also remember is that suppose I have found a second integral I for my Hamiltonian system, then any function of the integral is also an integral. Because the derivative of the function with respect to orbit is the partial derivative of the function with respect to the integral times the integral derivative along the orbit, which is of 0. And so this is 0. So that's what an integral of motion is. So now let's ask what an integral potential is. And this is a so-called Liouville's theorem. Liouville's theorem says that a Hamiltonian system with n degrees of freedom, that means in 2 n-dimensional phase space, is integrable if it has n independent integrals in involution. And involution means that they're all, if you put them in the Poisson bracket, then between all the integrals, the Poisson brackets give 0. And then this system can be integrated by quadrature. So our phase space in galaxies is typically 6-dimensional. So we have 3 velocities and three coordinates. And so we need 3 independent integrals of motion to make the system fully integrable, one of which is the energy. So now suppose we have such an integral potential, so we have 3 integrals of motion. Then it can be proved, and this is in Arnold's book on classical mechanics, that the surfaces defined by those n integrals of motion, I1 to In, set each to some constant value, some numbers, are so-called n-dimensional tori. And an example of a torus is shown here. So this if you like, you can say mathematically it's a product of n circles. That's not very helpful, and it's sort of difficult to do because here I've tried to put some on paper, and so that's not the right medium for plotting these tori, but still. So this is one cross section through the torus, and then this is the other cross section through the torus. Because I can only do a perspective drawing on a two-dimensional piece of paper, it looks like those two directions are different, but in fact they should be exactly the same. So in each direction, my motion is on the surface of the torus, and there's two independent, what's called loops around the torus. One is this one here, and the other is the second one. And if I have a three-dimensional torus in a six-dimensional phase space, I have three independent loops around the torus. So the other thing that follows from this is that on the torus, the motion is quasi-periodic. Each angle variable, we'll come to in a moment, evolves linearly with time and gets you around this independent loop here. So that's one angle variable, and that's the other angle variable in this example. And they evolve independently and linearly with time. And so on this torus, you can define a coordinate system called angle action coordinates, theta and j, theta the angles and j the actions, where the actions are constant on the torus, so they're function of the integrals in principle. And because they're function of the integrals, they also time independent. And the angles have the property that their Hamiltonian derivatives are equal to the frequencies, and they're not zero. This is wrong. And so given that the actions are constant, also the frequencies are constant on the torus, and therefore the angle values evolve linearly with time with their respective frequency. And when you want to evaluate them, the action variables, you can do that by integrating the quantity p dot dx along the independent loops on the torus. So there's one integral like this, and there's one integral like that, and then there's a third one. And it turns out that whatever shift you do of the loop around the torus, it doesn't matter, it adds zero, provided it stays the integral on the right, on the same loop.
The frequencies are zero?
No, I'm sorry, this is a mistake. They're constant, yeah. So that's what an integral plane is Liouville's theorem. So if I have n independent integrals in involution, then all these things follow. I can define action angle variables, my system is integrable, etc. So again, the same mistake here, sorry, so cut out this equals zero. So that's my Hamiltonian equations again for this action angle coordinates. My omegas are the orbital frequencies, and they're constant on each torus. And I've already said that. The angle variables evolve 2 pi periodically, linearly with time. And then if I have it means then that basically I can expand any of the phase space coordinates as a Fourier series in terms of the n dot omega t plus some phases. And so any orbit can then be expanded as a quasi-periodic function of time. I want to just give you one little example. This is the harmonic oscillator in one dimension. So here's my Hamiltonian, half p squared plus x squared. Then I can solve that, and I'll find that this is going to be equal to 1/2 j, where the j is basically the integral p dx around the orbit. And so p turns out to be the square root of j times cos theta, and x turns out to be the square root of j times sine theta. So that's my complete description of the orbit. And what I've assumed here is that the frequency was 1/2, because my dh dj is 1/2, that's the frequency. And so the angle around the orbit of this harmonic oscillator in phase space evolves from some initial phase and then linearly with t with frequency 1/2. Okay, I wanted to not use action angle variables too much more, but I wanted to tell you what they're useful for. So later we'll see that actions can be defined also when my system is non-integrable. That's a great advantage. They can be defined for isolated tori. Secondly, actions like angular momenta have the property of adiabatic invariance. So that means if I slowly deform my potential, that their values remain approximately constant. The angle variables, they're a natural point to label where the orbit is on the torus. And if you want to do perturbation theory of orbits with, let's say, potential perturbations, then the best way to do it is in action angle integrals, action angle variables. So now let's come to orbits in a slightly more complicated systems. And now I'm going to discuss non-axisymmetric planar potential. That's sort of the next most simple case where something new comes in. Now, what comes in new is that in general, those non-axisymmetric potentials are no longer integrable. So sometimes you can get a solution by some perturbation theory, but generally in these potentials, you cannot find orbits analytically anymore. You have to integrate them numerically. Now, yet it is true, as you'll see in a moment, that many of the orbits look like they might be still integrable, and therefore you might say the potential is perhaps near integrable. And that's one of the interesting results, actually. There was no guarantee that many of the galaxy potentials would turn out this way, but it has turned out that many galaxy potentials appear to be nearly integrable. So I'm going to use those to illustrate some general points. And one of them is this Book's loop orbit structure that is quite common in triaxial potential, and I will illustrate it using a Stecker potential. And then one of the new things that comes in is that in addition to these what we call regular orbits, you also start having so-called chaotic orbits, orbits that manifestly don't respect integrals and cannot be described by action angle variables anymore.
So in other words, it's not generally true that non-axisymmetric potentials are non-integrable.
No, there are isolated cases. I'll come to that in a moment. There are a few special cases, yeah. But it's almost generally true. Okay. Yeah. So I wanted to go through this integrable case, this special case first. Show you, yes, there are some. So this is due to the ZEO in 85, and goes back to some work of Donald Lynden-Belz in the 1960s, and even to I've forgotten Steckel's first name, but he was a German mathematician around 1900. So this works by defining a special coordinate system. Often, as you know, it's important to use the right coordinates to solve the problem. And these coordinates are elliptical surfaces for lambda. So kind of these surfaces lambda equals constant. And then the other coordinate here in this two-dimensional case is mu, which describes these hyperbolae here. And the potential has the special form. So as a function of these coordinates lambda and mu, it's given by some function of lambda minus same function of mu divided by lambda minus mu. And if you make these assumptions, then there exists an exact second integral I2. And this integral is in such a way that it confines the orbits between coordinate surfaces, just like in the spherical case, where an orbit was going between an inner and an outer circle in the plane perpendicular to the angular momentum vector. So here, the orbit is confined between coordinate surfaces, but now there are surfaces in lambda and surfaces in mu. For example, one of these green orbits here is confined between these two values of lambda and these two values of mu, and that gives rise to what's called the box orbit. You can see why the name, because of this box-like behavior here. If you have that orbit go a little further out along this axis here, you end up with an orbit of this kind here. That's a typical box orbit in such a Stecker potential. And then there are also orbits that go out in the mu coordinate further, so you can have them going up to this kind of coordinate values, and then you end up with an orbit that's bounded by this kind of surface. It's the larger orbit underneath the also box orbit, but one that looks a little less boxy than the previous. And then finally, you have orbits that can go all the way around, so they have no limit in this mu coordinate, but they are confined between lambda surfaces. Yeah, and that's what's called the loop orbits, and they have this typical shape. Now they're a bit like circular or perturbed circular orbits in spherical potential, except they're elongated in this direction, and they're elongated in the direction perpendicular to the principal axis of the potential, which is this way. So mathematically, you can see these things by writing the momenta in these coordinates as a function of the energy, the integral, and some of the parameters of the potential. And then you can work this out. But geometrically, this is what you find. So these are exactly integrable orbits in a special potential that have either a box-shaped form or a loop orbit form. That turns out to be general for more general two-dimensional potentials, except that these orbits are no longer integrable. So if you want to understand orbits in more general potential, then given there's no integral, you can't do it analytically anymore. You use a tool called the surface of section. And that's basically a mapping from phase space onto phase space. So in this case, let's take a two-dimensional potential. My phase space is four-dimensional, but I know the energy is conserved. So I have three free parameters. Now, if I say I'm looking at the orbit only at moments when it goes through this plane here, let's define this plane to be, let's say, Q2 equals 0, then I have in principle now two free parameters. So a general orbit that has no further integral but energy will therefore, in this plane, fill a two-dimensional surface. If my orbit has a second additional integral, then I have three conditions on this plane. Energy is constant, the second integral has some value, and Q2 equals 0, so that's three conditions. So those orbits are then on this surface defined as one-dimensional lines. And then if I have, for some reason, a third constraint, which sometimes happens because, let's say, of a resonance, then on this plane I have a one-dimensional set of points, i.e. points. So now here look at these surfaces of section. This is now for one of these, I think, logarithmic potentials, if I remember right. And now we're integrating orbits numerically, and we're recording their positions in the surface of section at always the time when it goes through this plane at a positive velocity. And you can see two things.
Useful to explain the axes.
Have I not? So one axis is the coordinate, the other coordinate, not Q2 equals 0, but Q1. And then the second axis would be the momentum in that, or the velocity in that direction, V1. And then Q2 equals 0, and the V2 velocity is positive and is given by the energy at any point when the orbit goes through the surface of section. So this is a set of orbits, integrate numerically, and you can see, surprisingly, that they all seem to lie on what's called invariant curves. These are these one-dimensional curves here in the surface of section. They're not completely filled now because I've only integrated for a finite amount of time. But the orbit so typically goes from here to here to here and so all around. So if I integrate for very long, I will fill these curves continuously. So I said just now, a one-dimensional curve in surface of section means that there are three there's three conditions satisfied, one of which is the energy is constant, the second is that I'm in this plane, and the third must then be that this orbit is confined by a further quantity, which for the moment, let's call it an integral, second integral. And then as you go to the center of this invariant curves, here you find a single dot, and that's a periodic orbit. So when you do the same surface of section for this previous Stekel potential, then these kinds of orbits here, they translate into these loop orbits here. And if you reverse the rotation direction of the center, then they go to the other side. Whereas these kinds of orbits, so-called box orbits, they go to these curves. And you can also see there is a transition between the two families. And this transition happens when the two branches here, or the two sides of this wedge, merge on the axis, just like when a pendulum reaches the top. That's the sort of similar behavior. The surface of section shows quite similar behavior to these separate potentials, as you see, where these are the box orbits, and these are two families of loop orbits with different sense of rotation. Now let's go a bit away from the easy cases, and this one is now a surface of section for a similar two-dimensional potential, except that I have increased the central mass concentration. So I've now put in a cusp in the stellar density. And so here you see now, still there's these two families of loop orbits. There's also some of the box orbits left. But there's a lot of now so-called resonant islands that appeared in the phase space. These are now orbital families that cannot be described by anything like this separable potential that I showed you. But they appear because of the more cuspy structure of this potential. And later, I'll show you also that there's also some chaos in this surface of section, even though here it's not plotted. So that's the surface of section. It's a useful tool to study orbit structures, and here is so what I said in words. Now mathematically, energy is this function here, the 3D surface. Surface of section is a slice, so the remaining space is two-dimensional. And then closed orbits correspond to a finite number of points in the surface of section. Non-closed orbits with the effective second integrals to these smooth invariant curves. And stochastic or chaotic orbits correspond to a distribution of points that are in a two-dimensional area. So it's a useful tool to understand orbits in two-dimensional potentials, mostly. So let's now take a more abstract point of view. And I just want to briefly tell you about some theorems from nonlinear dynamics that explain some of this behavior. I won't be able to explain them really in the right terms. So this is a very highly simplified description. And if you like to look at them, then go to Arnold's book on classical mechanics. So one of the theorems is that almost all Hamiltonians are non-integrable. And by almost all, the mathematicians mean that the set of integrals has measure 0 in the space of all integrals. So it's a tiny fraction. It's not worth talking about, basically. So that's the second theorem is the Kolmogorov-Arnold-Moser theorem, very famous theorem, for near integral potentials. So what they did is they considered a Hamiltonian H that was close to some integrable Hamiltonian H0. And so they showed that if H0 is integrable and the perturbation epsilon is sufficiently small, then most of the orbits in this perturbed Hamiltonian will still lie on surfaces in phase space that are tori. Am I over time?
Yes.
Oh, I'm sorry. Yes. So I should go through this and stop. Yeah. And this is quantified by saying that the measure of the phase space that's occupied by tori goes to 1 as the perturbation epsilon goes to 0. And so that's what it means, most orbits still lie on torus. So that's encouraging. It means I can perturb my integral potential and I can get many orbits to lie on tori if my perturbation is sufficiently small. The additional result is the so-called Poincaré-Birkhoff theorem, which says that orbits become first irregular or chaotic, meaning the tori break up in phase space, near the resonances of the unperturbed integrable Hamiltonian. This I want to illustrate you on this plot, and then I finish. So here's my integrable system originally, and it had all these tori. Now I make a perturbation, and what you find is around this resonant torus, orbits become now complicated. What happens is that this torus surface breaks up into a number of resonant islands, depending on the resonance that this torus had. And in between those resonant islands, you will find some small amount of stochastic chaotic orbits at first when the perturbation is very small, which then grows as the perturbation grows. And you can see that this is a phase space diagram for a pendulum, momentum versus coordinate. So you could view those resonant islands here as subsequent stable points here. You can see that if you're sufficiently close to one of these islands, then your motion will be around this so-called fixed point, the periodic orbits, just like here. And if you're sufficiently far away, it'll be on this orbit going all around, which is something that is still preserved from the structure of the unperturbed Hamiltonian. But then there's this boundary region where in the pendulum it's exactly integral. You reach this point which is just on top. So the pendulum is going up and then it's falling down on the other side rather than on the same side. But that motion becomes unstable as I perturb my potential. And so in one way of colloquially saying this is that orbits near this transition, then after a while, they don't know anymore whether they belong to this orbit family or to that orbit family. And then they chaotically explore a region of phase space around this so-called heteroclinic orbit here, which is in the pendulum analog is the one that takes the pendulum right to the top. And so when you think of perturbations of integral potential, this is how the phase space starts breaking up and chaos starts to appear. Okay, I think that's probably enough for today. Sorry for running